This is lecture 23, and the topic of the lecture today is KPCA, or Kernel PCA. And Kernel PCA is going to be the extension of the basic principal components analysis technique that we originally learned. And so since that is one of the kind of most useful techniques for unsupervised learning, and you see it crop up all over the place for supervised learning, I think a nice extension to KPCA is to talk about a slightly more advanced version. And the problem that KPCA is trying to solve is that for PCA, we're only going to be able to recover a linear subspace. So an example I think here is illustrative, where if I have some data, maybe I've measured two variables, x1 and x2, and maybe my data basically lies on some circle. So here are the actual data points I measure in red, and they're basically on, so x is a data point, they basically lie on some circle. Now, technically, this data is two-dimensional. I technically need an x and y coordinate to fully describe this data. And so if I were to try and run PCA on this, we really wouldn't be able to reduce the dimension of this data because it doesn't live in a nice linear subspace. For 2 dimensions, a linear subspace would be just a line. For 3-dimensional space, a linear subspace would be a plane or a line. And so you can imagine that data might live in basically some kind of non-linear subspace, what we'd call a manifold, which is basically the generalization of a subspace where it doesn't need to be a plane, for example. Nonetheless, in our example, we have the intuition that this really isn't fully 2-dimensional data, because it basically just lies on some circle. And so if alternatively I were to just think about my data as being described by some angle, I actually would only need one number to describe my data, basically, because it's basically, my points are just, if I just tell you the angle they're distributed at, I basically know everything about how the data is distributed. And indeed, if I were to convert this, say, to polar coordinates, what I would get is a space in polar where maybe r is the radius and theta is my angle, and this would go, say, 0 to 2 pi. Then my data would basically lie on some line where, the radius r would define where it is on the r coordinate axis, and it would basically just span 0 to 2 theta, and my data points would look like this in a polar coordinate space. And so this is a one-dimensional subspace where my data could be summarized basically using a one-dimensional subspace of a polar coordinate space. And so under the right transformation, you can see that my data is really just one-dimensional. And so the problem that Kernel PCA, or its kind of slightly simpler version, non-linear PCA, is it's trying to answer the question of, if I embed my data into some, and we're going to say potentially high-dimensional space, using or through some transformation, maybe if I pick the right transformation and I embed my points not in the original space but in some transformed space, and this transformed space might be particularly high dimensional, In fact, we might increase the number of coordinates. It's possible that maybe, question mark, I can better summarize my data using PCA. So in our case here, this allows us, we embedded it in the polar coordinate space, and then we can do a dimensionality reduction, and we find it's basically one-dimensional. Alternatively, you can think about it as I'm allowing my PCA to learn not only linear subspaces, lines, but nonlinear subspaces. And so because I picked a polar coordinate transformation, I can learn circles or ellipses or other things like that. And so I basically learned this circular subspace in my data by embedding it first into a nonlinear transformation of my data and then doing dimensionality reduction on that. And sometimes it pays off to take your data and embed it in a really much larger space, do a whole bunch of nonlinear transformations to it, which somehow seems counterproductive because we've increased the dimension. But it's possible if I embed it into the right nonlinear, bigger transform subspace, that when I do my dimensionality reduction, I actually get a smaller subspace than I would if I had just done PCA on my original data. So that's a bit of a twist, but we'll see that that is true and very powerful. So the first kind of basic technique that I want to talk about is called nonlinear PCA. And we can very easily extend nonlinear PCA to build something called kernel PCA. And here, I'm gonna warn you right up that word kernel in this lecture is quite a different word kernel than the last lecture. So this word is way overused in mathematics. And the kernel of last lecture doesn't have a lot to do with the kernel of this lecture. So that's unfortunate, but that's just the way it is. So nonlinear PCA. So we're going to start with our data x. And x is going to be n by p. I have n observations of p variables. And I can think about this thing row-wise. So that my rows are my n observations, and each of these x sub n's are in some p-dimensional real space, are my observations. So the observation is my p variables or features. And I'm going to consider some embedding map or function, and I'll call it phi. And this is going to be a function that takes our xn's, which are in Rp, and is going to put them in some other, let's say, d-dimensional space. So typically here, d is going to be much larger than p. Doesn't have to be, but typically what's going to happen is we're going to embed the data through this mapping phi into a much larger space, do PCA in that much larger space, and it will actually reduce our dimensionality of our data better, which can be interpreted as basically learning, instead of linear subspaces in the original p-dimensional space, as learning nonlinear subspaces in that p-dimensional space. So we're going to form, using this embedding map phi, we're going to form a new data matrix, the embedded data matrix, capital phi, which is now is there n observations embedded in this d-dimensional space, where the rows now are phi of x1, phi of x2, all the way down to phi of xn. So this is our embedded data matrix, embedded in this larger space. And the idea with nonlinear PCA, let's just call it NL PCA, is that what we want to do is we want to do PCA on this embedding. So what we could do is we can form this embedded data matrix and pretend like that was our original data matrix to start off with and do PCA on it. So what would that look like? Typically in PCA, we first will center our data. So the kind of 0th step here is to form our embedded data matrix. Capital Phi. Then we're going to want to center this, because typically you center things before doing PCA. So if I let phi bar be the average of my rows, basically the x bar of the embedded data, so all I'm going to do is 1 over n, and then I'm going to sum up my phis. So this is a vector in RD, right? And I'm going to form what I'm going to call phi tilde, where I'm going to subtract this thing off of each of my rows. So this is a typical way we do PCA, right? We would calculate the mean of the rows and subtract them off each of the rows. Or alternatively, we calculate the mean of each column and subtract it from each column. They're kind of equivalent ways of thinking about it. So we'll form that centered matrix phi tilde. Now I want to point out that as kind of an aside here, that, and I think I pointed this out a little bit before, is that phi bar can be written as 1 over n times the inner product between a vector of all ones, let's call it 1n. And so the inner product between that and our data matrix phi, right? So if you think about what's going on here, this, we'll take the first column of phi, take the inner product with a bunch of ones, which just sums up that first column of phi and divides by n. That would be the first element of phi bar. The second element of phi bar, the second column of phi, sum it up, divide by n. That would be our second element of phi bar, right? So this will correctly calculate the row-wise mean. So it would be a vector of the mean of each of the columns of phi. And so you can actually write phi tilde as my original embedded, so the centered embedded matrix is the original embedded matrix, but then we subtract off phi bar from each row, and I can do that by writing, if I take that another one of those vectors with all ones, and I look at the inner product between it and phi bar, so phi bar is basically a row vector, this thing is another row vector, and if I look at, I'm sorry, we want this thing to be a column vector, there we go. Now this should correctly subtract that off, and you could write this as, of course, I could expand out what phi bar is. This would be minus 1n times 1n transpose times phi, or I could write this as the identity minus 1 transpose. Whoops, I'm forgetting an n here, aren't I? Got to divide by n here. Divide by n times phi. And this thing is called a centering matrix. And we're just going to call it Jn. This is our centering matrix. So if I multiply phi by the centering matrix on the left, it will center the rows of phi. If I multiply by j on the right, it would subtract off the column means, as it were. Whatever way to want to think about it. But It's basically a center matrix. It's a symmetric matrix, but it's an operator. So it turns out this whole centering thing, maybe not too surprising, is a linear operator. And so you could view this centering each of my data points as a matrix multiplication by this J. And that's just a little bit of linear algebra to convince yourself you can write it that way. So as the aside, the main point here is that what are we going to do? Basically, we form our embedded data. We center the data to form v tilde. And then we do the SVD of it, right, to get basically the principal components. So we say phi tilde is maybe u sigma v transpose. So here this sigma is my diagonal matrix with my singular values in it. I'm using sigma because I've already used the d as the dimension up here of my embedded space. And then the fourth step is that I want to form my principal components. Usually I called those z before. What do? We take phi tilde and we project it onto that space. So we take the first q columns of v, and this will give us z. And so here, this thing is matrix. It has my n observations, and it has q columns. So this is basically what people call nonlinear PCA. Is all you do is you have some embedding map, you embed your data into the higher dimensional space, and then you do PCA on that. So we can look at an example of how one might do this. So here, let's just say p is equal to 2. So I have 2 variables per observations. So an observation, xn, is xn1, my first feature, xn2, my second feature. And let's say phi of xn, my embedding map, is going to embed this in a 3-dimensional space. So we're going to say d is, we're going to embed this in a 3-dimensional space. And what do we want a 3-dimensional space to be? So all this phi is some function of the elements of xn. So let's say the first one is xn1 squared, so the first element of xn squared. Second one is xn1 times xn2, so it's like an interaction term. And the third one is xn2 squared, so it's like a quadratic term. And actually, I'm going to multiply by root 2 out front for this. It doesn't really change the transformation, but there's a cute little math simplification if we do this. So that's our embedding, and you could call these z1, z2, z3. These would be the coordinates in that new 3-dimensional space. So if I've taken my original picture where I have my 2 variables and I have my data points that are kind of arranged in a circle, then my data points here live in some circle. So my data satisfies exactly if they exactly lie in the circle, or kind of approximately if they approximately lie in the circle. The following relationship, there's some a, b, c, and d, where a x n1 squared plus b x n2 squared plus c x n1 x n2 plus d is 0. Why does it satisfy this? This is just the general equation for a circle, or technically a conic section, but a circle. Certainly all circles have an a, b, and c that satisfy this. And so if my original data lives, or at least approximately lives on a circle, it'll satisfy or approximately satisfy this relationship. And in my two-dimensional space, this defined a circle, basically a circular subspace. If I transform this through phi, I can rewrite this in terms of z1, 2, and 3. This would be a z1 plus b z2 plus c z3 plus d is 0. And what is this the equation for? In the three-dimensional space, this is the equation for a plane, right? So what I've done is I've embedded these points into a three-dimensional space, z1, z2, z3, and somehow the circle exists here, and I have my points, but I've embedded these points into a three-dimensional space, and you can see that these points now live on some plane in a three-dimensional space by dint of the fact that we know that an equation of this form defines some plane in 3 space. And so what does that mean? We can recover these as a linear subspace. So in the original case, these didn't live on a linear subspace in any meaningful way. Now they truly live on a two-dimensional linear subspace of a three-dimensional space. And so what I've done is by doing the correct transformation, I've embedded these from a two-dimensional space into a higher dimensional space. And in this higher dimensional space, they live on a plane because I've chosen my embedding well. Now, this example is a little bit silly because I've gone from two-dimensional data to three-dimensional data, but it lives in a two-dimensional space. So really actually reduced the dimension of my data. I've gone from 2 dimensions to 2 dimensions. In more realistic examples, or you would go to a higher dimensional space. You'd have a more complicated set of points. You go to a higher dimensional space, and then when you come back, you actually get a better dimensionality reduction. And we will definitely prove that by the end of this, that you can do that in many cases. If I had chosen a different embedding, say I had chosen a polar embedding, as we had originally shown, I would get a one-dimensional subspace. So it does depend on the embedding a bit, exactly how to do this. Okay. So let's talk about what this is, how this procedure is kind of shaking down here. So I calculate my PCA using the SVD, right? This is what I was trying to impress upon you. And the SVD, again, is one of the most useful things. You see it showing up all over the place. You saw it show up in ridge regression, PCA regression, PCA. We saw it show up or you can show it shows up in kernel regression. There's a particular way you can show that, or I guess smoothing splines, maybe not. Well, let's say it shows up in splines. You can show it shows up as a certain basis of splines. You can view through PCA. So SVD is maybe the most important mathematical theorem, period. Maybe more important than the central limit theorem, arguably. Certainly for some of these computational things. And so this is why I hit this topic over and over and over and over again in an applied class like this, because you can understand many, many procedures much better if you decompose things with SVD. So in particular, when we do our nonlinear PCA, right, what we do is we decompose phi tilde, which is this n by d matrix, embedded data matrix. We decompose it as u sigma v transpose, right? And the elements of u, these eigenvectors of u, are calculated from what is called the left gram matrix, which is phi tilde transpose. So this is called the left gram matrix, named after a guy named Graham. And this is going to be an n by n matrix. And the elements of V we get from the so-called right gram matrix, which is phi tilde transpose phi tilde. Right, we get the eigenvectors from the right gram matrix. That gives me the elements of V. The eigenvectors of the left gram matrix gives me the elements of U, and the eigenvalues of either of these, turns out they're equivalent for non-zero eigenvalues, give me the elements of sigma. So when I want to calculate, so this is kind of the SVD of this thing is kind of a centrally important object of study. When I want to get my principal components, right, eventually I calculate basically phi times V, or phi tilde times V. And if our phi is U sigma V transpose, then that's equivalent. If I want to basically do phi tilde times V, this is going to be U sigma. And maybe I truncate after Q of these because I don't want Q of the components or something like that, right? So this is maybe the overarching equation for the singular value decomposition, which says that I can transform in a certain basis of my row space and column space. But notice that if I want to calculate, say, phi times V, which is what I say I want to do, I have to actually calculate phi tilde transpose phi tilde. And this is a D by D matrix. And I have to do the eigen decomposition of that. Whereas phi tilde transpose is an n by n matrix. And so typically, this is more attractive to use because typically n is much smaller than the dimension of the embedding space. And if I want to calculate phi tilde V, I could alternatively just calculate U and sigma, and that would give me the same thing. So I could either calculate V and multiply on the left or on the right by multiply phi tilde on the right by V, or I could calculate U and get sigma. And doing this, calculating this whole D by D matrix, if this D is large, like 100, that would be incredibly large, and I have to do a whole eigen decomposition of it. Whereas my n is typically going to be smaller, so the n by n matrix can be small, you do an eigen decomposition of it. So instead of doing phi tilde V, I could just look at U sigma. And I can get the eigenvalues, I can get the sigma, because you can recall that sigma I is the square root of the eigenvalues. Lambda I is the eigenvalues of either the left or the right. So I can get the sigma matrix by looking at either. Sigma is easy to get, but instead of calculating V, which is hard to calculate because it's a huge D by D matrix, I can get the smaller U. So, right, so let me just write that down. So alternative to calculating Z, which we said is phi tilde by V 1 to Q, I could calculate Z as U times sigma, and I could just pull off the first Q columns of that. And if by eigen decomposing this left one, phi tilde transpose, if I eigen decompose that as U lambda U transpose, then U sigma, the first Q columns of U sigma is first Q columns of U times the first Q columns of lambda to the 1/2. So that's a cute little trick. It's a quicker way of calculating things, where I don't actually have to calculate this huge d by d grand matrix to actually calculate b. I could just get the smaller one. Notice that the dimension here doesn't actually, the d doesn't show up. It only kind of shows up implicitly because I have to calculate this phi tilde, right? But the dimension of phi tilde transpose is actually m by n. It's not d by d. So I've kind of hidden that dimension of that embedding space, which is large and potentially cumbersome. I've kind of hidden it away. So the quick version of nonlinear PCA would be to kind of 0 calculate phi tilde. 0 is calculate phi, so calculate my embedding data matrix. Step 1 is I center it. So I multiply on the left by my centering matrix, something like that. Step 2 is I calculate what I'm going to call k, which is phi tilde transpose. And I'm going to eigendecompose k as u lambda u transpose, and then I can get my principal components, my z's, as u, the first q columns of u, times basically the first, well, the subdiagonal matrix, let's call it, let's just call it lambda q. This is basically, be really precise, it's the diagonals of the first q lambdas. It's kind of a truncation of the diagonal, and then I take it to the 1/2 power. So in fact, I'm going to throw in the square roots there. But this is my kind of quick PCA. So this again is n by n, which hopefully is quicker to calculate. And this thing is going to be called my kernel matrix. So we've introduced this word kernel now. And it's n by n. And so I've avoided this huge dimension, potentially that's troublesome. But I still have to calculate. And my first step, I actually have to embed my data in this higher dimensional space. So I still haven't quite avoided having to deal with this large dimensional space because I still have to embed my data there, first off, and then I have to center it. But then I can kind of hide it in my kernel matrix and then only do an eigendecomposition of an n by n matrix, cool, to get my principal components. So it's not quite as quick as I want because I still have to go through and work with this really high dimensional space to actually embed my data. And if I'm working with 1,000 dimensional space, now I have 1,000 dimensional column matrix phi, capital phi here, and that's not great. And so the question is, can I avoid this thing altogether? What if I were able to just start at step 3 using some k that I could calculate without needing to even know this embedding? So this seems like a bit of magic. But if I could do this, I wouldn't even need to know my embedding. I wouldn't even need to know what technically the data looks like in embedding. If someone just walked up to me on the street and gave me this matrix K, this kernel matrix, I wouldn't need to know what the data actually looked like, that embedded space. All I need to do is take the matrix K, do the eigendecomposition, and then do this little magic to get Z, and that would be basically the data that was projected up, embedded up into a higher dimensional space and then projected down to a subspace. So it would do the whole procedure for me. And it would avoid me ever having to actually deal with the high dimensional space because K is only n by n. It only depends on how many points I have. And so if somehow someone walked up to me on the street and gave me K, we would be set. I would never actually have to deal with potentially a large dimensional cumbersome space. And I would be able to do this really fast if I just started with step 3, basically, and just did that eigendecomposition. And so the question is, can I do that? And the answer is yes. In pretty much all the cases we're going to care about, you never actually need to know the embedding. And this is an incredibly powerful theorem from functional analysis that says we don't actually need to know what the embedding is. All we need to know is this kernel matrix. And this is basically what's called the kernel trick, because it's a little trick that allows us to avoid ever dealing with the embedded space, which is high dimensional, hard to compute. And we'll see, actually, you can work with an infinite dimensional space, which you could not actually compute. And so we could project, we can embed our data into an infinite dimensional space, get a finite dimensional subspace of that, which would be impossible if you actually had to work with the embedding, but you don't. The mathematicians have told us that we can avoid it. And so this is what's called the kernel trick, because somehow I've tricked my way out of actually having to deal with the embedding. So let's look at why that could possibly be true. So let's look at our example again. So if you remember, our example embedding map was something like this: xn1 squared, root 2, xn1, xn2, and then it was xn2 squared. This is our embedding map. And let's just assume that, phi has been centered. Let's not deal with the centering issue right now. It's actually not a big deal, and we'll deal with it at the end. If we ignore that whole centering step, then my elements of my kernel matrix, my K matrix, what do we want to call it? N prime? Does that work? M in N, and let's call it N and N prime, right? So it's like observation N and observation N prime, right? So if I look at that element, this is, what is my kernel matrix? I said it's just phi, and we're just going to ignore phi, the tilde for now. We're just going to assume this thing has been centered. So it's phi transpose, and it's the NN prime element of it, right? And so what is that? What's the NN prime element of the product of matrices? It's the row of the first one times the column of the second one. So it's row n of phi transpose, or dot product, with column n prime of phi transpose, right? Which is row n of phi transpose row n prime of phi, right? Because I had a column of phi transpose the same as row of phi, right? So the elements of this kernel matrix, of this n by n phi transpose, are the dot products between rows of my embedded data matrix, right? And what do we call, what is the row, the nth row of phi, of capital Phi? It's the embedding of that nth observation. So this is phi of xn transpose phi of xn prime. So this is the dot product, dot prod between embeddings of data, of the observations. Now, up to this point, this has been, so just put this away in your mind here. Up to this point, this has been totally arbitrary for any phi. We have a particular embedding we want to look at, which is this thing, xm1 squared, blah, 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 right? So let's write out what those are. Let's actually just change colors just to make this clear. And in our particular case, the phi of xn is xn1 squared, xn1, there's a root 2 there, isn't there? Root 2, xn1, xn2, xn2 squared, transpose. And our second vector is xn prime 1 squared, xn prime 1, xn prime 2, there's a root 2, I always forget, and then there's an xn prime 2 squared, right? The dot product between those. and we expand out what that dot product is. It's xn1 squared xn prime 1 squared plus 2, my root 2 is multiplied with 2, xn1, xn2, xn prime 1, xn prime 2, plus xn2 squared, xn prime 2 squared, which looks horrible, but I'm going to claim is just xn transpose xn prime quantity squared. And I'll let you think about why that's true. But if I look at the dot product, or the inner product between the nth observation and the n primeth observation, that will, and I square that thing, that will exactly get this line, because it's basically this thing. And I'll just do one step for you, right? The inner product is like xn1 xn prime 1 plus xn2 xn prime 2, and then I square the whole thing, and that will get me exactly that term. So it turns out that, what's my point here, is that the kernel, the element of the kernel matrix, which is the dot product between the embeddings of the data, I've made phi disappear. I've made the embedding disappear, right? The only thing I need to calculate my K matrix is I need to take dot product between my original unembedded data, which is p-dimensional, and I square that. So only need original data to calculate elements of K. No embedding required. I don't need to know the phi. I don't need to calculate phi of xn. All I need to do is take my two original points, take their dot product, and square that thing. And I do that over all pairs n and n prime, and that will give me all the elements of my kernel matrix. So I never actually need to go into the embedded space. I don't need it. I don't need phi. It's totally dropped out of my equation here. And so is someone going to walk up to me on the street and give me this kernel matrix K? No. But it's actually not that hard to calculate. I don't need to embed my data. I need to calculate the capital phi matrix. I don't need to know what the embedding is. All I need to know is that if I were to use the embedding defined by this, which is a particular embedding, then if I wanted to calculate K, I actually don't even need to plug my data in this phi or make that big capital phi matrix or center it, whatever. All I need to do is I need to take the dot products between my pairwise between my observations, square that, Bob's your uncle, we have the elements of K. And so it's actually really easy. I stay with my smaller, my original p-dimensional space, never go into the huge d-dimensional space. So this is a trick. I mean, it's a trick that works, but it's called the kernel trick. So let me write this again. I don't need phi. I just need a function K. We'll reuse K here. Oh, maybe we'll make it a lowercase k for fun. I just need some lowercase function K that takes two vectors, x and y, and calculates the inner product between their embeddings. So more generally, for any embedding, what we said is that the elements of this K matrix are the inner products between the embedded data. So if I had some function, in this case we have the function, this thing here is basically K of xn1, or sorry, K of xn prime. But in general, if I could maybe find some little function K that directly calculates the inner product between the embeddings, but don't actually need that phi, which we could do at least in one case, then we're great. We don't actually ever need to work in that larger space. And so I can work with any arbitrary large space, and I'm not going to pay for it computationally. Not really. So in general, this is going to be doable for many embeddings. So examples of this, we had our first example, which is like a phi of some vector was the first element squared, the square root of 2 times the product of the two elements, and then the second element squared. And so here p was equal to 2, and this embedded us in a three-dimensional space because I had 3 elements of this vector. And we knew that our kernel function, which is what this little k is called, between 2 elements, in order to actually calculate the inner product between the embedded data, all I need to do is know this little function here, which was the inner product of the original data point squared. So this is maybe example 1. We could play this for other things. What if I look at all monomials of degree 2? So like, so what if p is larger, some arbitrary p, and I look at like a1 squared, a1 times a2, a1 times a3, a2 squared, a2 times a3, a3 squared, right? So I can look at embedding into all monomials, let's say all degree 2 monomials. So here, D is going to be what? It's going to be p plus 1 choose 2. And you can think about why that's true. It's kind of a combinatorial problem. But that's a huge space, right? That's like the square of p. So it's like squared larger. So go from a p-dimensional space to a p squared, something like that, dimensional space. And it turns out that in order to calculate the inner product between things under this embedding, and if I can calculate the inner product between things under the embedding, I can calculate my K matrix, and I can do a nonlinear PCA, or in this space. All I need to do is look at this thing is still K of xy is the inner product squared, right? So it's the same thing, but this works when p is bigger than 2. And let's keep going. Let's look at another example. Maybe my embedding is going to be all, I'm just going to say all monomials of degree, let's say m. If I did this, then I would go from some p-dimensional space to D would be, the dimension of the space is m plus p minus 1 choose m. This is like factorially large dimensional space. And it turns out if I want to embed into my embedding function is, I look at all degree m, so like maybe cubed, like a1 squared times a2 cubed, a1 cubed, a3 cubed, a3 times a4 squared, right? So all degree 3 monomials. Turns out there's a little function, a kernel function, that can calculate my kernel matrix, and you guessed it, it's just the transpose, the inner product between my original data points in the original low dimensional space to the mth power. So generally, we're going to be able to do this for a huge class of embeddings, where I can do this whole procedure. I don't even need to ever see the embedding. All I need to do actually know is the kernel function. So this is what's called the kernel trick. And this is basically a follow-on from a theorem called Mercer's theorem. And this basically says we can do this generally. And specifically, what it's going to say is that if I have some function little k, and it's going to take, it's a 2-variable function. So it takes me from R2 to R. And it has the following properties. One is it's symmetric. Symmetric, which means k of xy is k of yx. 2, it's going to be what's called positive semi-definite, which is a little bit more of a technical condition, not that bad, which basically says if I have some function f and I integrate kxy times fx fy dx dy, this thing is always positive. This is a very similar condition to what's called positive semi-definite for matrices. So read up on that first. I'm not going to, it's kind of a technical condition. Basically means it's somehow nice. and it has to be bounded. So it can't be infinite anywhere. It has to be well enough behaved. So a function that satisfies these conditions is called a symmetric positive semi-definite kernel function. If I have some little function k, so we're kind of going backwards, where I start with this kernel function, then there exists some phi that maps, some embedding function phi that maps from my p-dimensional space to some m-dimensional space. I don't know what m, but some m, so that this kernel function between x and y is how you calculate the inner product in the embedded space. So the trick is, in order to do this thing, all we need to do is have some way of calculating the inner product in the embedded space. Like, you need a way of calculating inner product when you do normal PCA. You need a way of calculating the inner product in the embedded space. But the trick is, the kernel trick, which is what this is called. So this is called kernel trick. The kernel trick is that I don't actually need to go embed my data into the space to calculate it. Turns out there's functions that operate on only the original data. They don't actually need phi. There's just going to be a formula in terms of x and y, no phi required, that can calculate directly. And so I don't actually need to embed the data. I just use this backhand kernel trick to calculate it. And so what we're basically doing is that we are implicitly working in a high dimensional space without needing to actually calculate the embedding into the space. And it's a much kind of cheaper way to go about this. And so basically, people don't tend to actually talk about the embedding functions much. What they basically talk about is the kernel that we use. And implicitly, if I use the kernel, so if I use, my second one, which is all degree 2 monomials, so typically when you actually calculate the thing, you'll pick a kernel. Maybe you'll pick x transpose y squared. In the back of your mind, what's going on is this embedding into some high dimensional space of all 2-degree monomials and then projecting out in space, but you don't actually need to know that. You don't really need to know it. It just works. It just deals with it. It uses this particular kernel. Or if I wanted to work with all monomials of degree m, what you actually do in reality is when you run kPCAs, you specify the kernel, and you do the calculations with this kernel. It is implicitly basically working in this infinite dimensional space. And so it's kind of super powerful. One of the reasons it's powerful is because D can not only be large, but D can be infinite. So, for example, what if I work with a particular kernel, k, xy, which is for some constant gamma is just going to be e to the negative gamma times the Euclidean distance between x and y squared. So this is basically what's called a Gaussian kernel. I guess it looks basically like some Gaussian. Anything to the negative something squared is always called some kind of Gaussian thing. And this, you can show, satisfies your properties. It's a proper kernel. It's a SBSD kernel. Then, therefore, there is some embedding. Right? So you can actually run kPCA. You can say, well, I'm going to use this kernel. And the kernel has a certain amount of flexibility with it. And you do your calculations. You don't ever actually need to know what the embedding is. There is kind of implicitly you can think about what's happening is the data is being embedded in some high dimensional space and being projected down onto a lower dimensional subspace. And depending on the kernel I pick, you have a bigger or smaller dimensional space you're embedding into. For example, if you work with this Gaussian kernel, it turns out that the space you're embedding into is an infinite dimensional space. And you can think about that because you can think about the Taylor expansion of an exponential function is basically a sum of all polynomials. It's like x, what's Taylor expansion? It's like x is x squared, x cubed, x fourth, x fifth, right? And there's some factorials in there, right? That's a Taylor expansion of an exponential. And so this Gaussian thing is basically expanding, and it's basically projecting your data into an infinite dimensional embedded space, and then picking a finite dimensional subspace. So you could not calculate the embedding if you wanted to, because it is an infinite dimensional space. And so this is incredibly powerful. So this is what's called Kernel PCA, which is basically a kind of direct extension of some of these nonlinear PCA ideas. Nonlinear PCA, you can literally do the embedding because you have some embedding map you define. With Kernel PCA, we don't actually explicitly define the embedding map. We just pick a kernel. Implicitly, it's defining some embedding in some high-dimensional space. We don't actually need to deal with it. So the last thing I should talk about before I kind of just write down the KPCA algorithm is centering. So I've kind of avoided centering, right? So really what we did was we wanted to calculate phi tilde, which was we multiplied our center matrix on the left by our embedding matrix, right? We did this for nonlinear PCA, which you can literally do because you actually calculate the embedding. And so in my KPCA algorithm, or let's go back to my nonlinear PCA algorithm, right? We actually straight up in step 0 calculated phi, we centered it, and then we calculated k, which was phi tilde transpose. So we basically want to work with some k tilde that is not phi transpose, but phi tilde transpose. But if phi tilde is j times phi, then this is j phi transpose j transpose, although j is symmetric. So this is just j, and that phi tilde was k, j. So if you want to actually center your data, actually what we work with is we take it, is we calculate k, and then we double center. We multiply it by the center matrix on the left, and we multiply it by the center matrix on the right. And that will give us a k tilde, which is as if we had calculated this thing from centered. So it's actually not a big deal. The KPCA algorithm, we can then basically summarize in a couple little steps here. So we're going to pick some dimension that we're going to project down onto, Q. We're going to pick a kernel, K, and implicitly this is picking some embedding, but we don't actually really need to worry about it. We don't need to deal with the embedding. And what do? We calculate K, so let's say calculate K, my kernel matrix. And how do I do that? The element, n prime, of K, we just have to throw our original data into this kernel that we chose. So we calculate K, we calculate K tilde, which is the centered version. Like this is basically as if we subtract off the mean. We just double center, we just multiply by the centering matrix on each side. And then we eigen decompose K as U lambda U transpose. And then we calculate our principal components, which is we get the first Q columns of U. And then we multiply by lambda to the 1/2, this Q version of it, which is basically the Q by Q upper left sub matrix of that lambda matrix. From the eigen decomposition, we take the square roots of these. And this gives us our projection. And so you notice here, we never actually dealt with phi. We specify the kernel, which had implicitly was doing some kind of embedding. And you could actually do that embedding if it's small dimensional, but if you're working with, say, a Gaussian kernel, you couldn't actually, because it would have been an infinite dimensional matrix. And then you double center it, you do an eigen decomp, Bob's your uncle. It's not that hard. The only thing you have to do is you have to be able to just pairwise calculate the kernel for your rows of your original data matrix, which is not so bad. And it does add a little more computation, but you can quickly kind of approximate that. So that's a real quick overview of a nice extension of PCA, the nonlinear PCA, or the even more impressive version, Kernel PCA. And it's a nice introduction to the kernel trick, which is used all over the place. I'll just say that the kernel trick is used not only, basically all we need to do is, you needed some way of calculating the inner product between the data points in the embedded space. And as long as your algorithm only depends on the inner product in the embedded space, we can always kernel trick it. So there are many other algorithms, PCA being one of them. The original PCA algorithm, you can see, only depends on the inner product between points. And therefore, if you were to embed it, the PCA, the SVD, only required the inner product between points now in the embedded space, and therefore we could kernelize it. There are many other algorithms that you can show only depend on the inner product between my training data, and therefore I can kernelize it, because I could, if I pick a kernel and replace the inner product with the kernel between my data points instead of the inner product between my data points, it is as if I've projected that data into a higher dimensional space and then done the math there. But I don't actually have to. So there are many other algorithms. For supervised learning, the most famous of this is support vector machines for classification. There's support vector regression for regression. But there are many other, you'll see kernelized versions of stuff, and that's what's going on. Turns out the algorithm only depends on the training points through the inner products with each other. You can kernelize it in this way and get a whole other class of algorithms. So I'll stop there. This is our nice introduction to Kernel PCA and the world of kernelizing learning techniques.